critical to draw a picture. So I'm going to start with, again, a very simplified picture. And we'll consider this object right here to be the stroller. And notice that she is pushing at a force of 110 degrees at an angle of 30 degrees with the horizontal. So she is not pushing straight away this way, she's pushing down like this. Right? That's most parents are not just as high as the stroller. I mean, there are some are, and I'm not denigrating those people. But usually the person is taller than the carriage. So this is kind of the way real life forces are applied. So the force comes in like this, with this angle right here being 30 degrees. And I should point out right now that my jokes are actually still funny even though there's nobody in the room. Just trust me, I'm still chuckling to myself. So this is 110 newtons going in this way. So now the baby and the stroller together, the baby is 9.5 kilograms and the stroller itself is 5 kilograms. So I'm just going to combine them like this. It's, it just shows that it's a baby and a stroller. It says that the coefficient of friction right down here is 0.14, and it looks like that's really all we need to start cranking this thing out. So again, start with a simplified picture, and now I'm going to draw in my forces, my other forces. So again, I'm just going to redo this one in red. We have a force of gravity going down like that. We have the normal force coming up like that. We have a frictional force. Yes, it's applied at the wheels, but again, this is a simplified diagram. This will be fine. A frictional force will oppose. And now those are all the forces, but I do want to point out that this applied force is applied at an angle. So there is, and again, this is why pictures are so important. There is an there's an X component to this force, and there's also a Y component to this force, and it is very, very important that you have the arrows indicating which direction those forces are. Absolutely crucial. Okay. So this would be my free body diagram. Again, it doesn't ask for it on number 7, but it is essential to understanding this problem. So the first thing we're trying to figure out is calculate the weight and the normal force. Well, that's going to be pretty easy. The weight, again, is the force of gravity that acts on an object. And the weight is always mg. And so in this case, the weight would be whatever, it would be 9.5, and it's asking for the weight. So this will be the baby and the carriage together. So 9.5 plus 5, that would be the m, and then g, which would be 9.8. Okay, so whatever this number is, of course in newtons because it's a weight. Now the normal force is a little bit different here. So this is why one of the reasons I picked this problem. Notice that the weight is not remember the normal force is a supporting force. It is the force that the floor provides upward to cancel out the force downward, right? Because we will all agree that the baby and the carriage are not accelerating upward into the sky, thank goodness. Neither are they accelerating down towards Hades. They are just motionless in the y direction, so the total of the down forces must equal the total of the up forces. And again, in the previous problem, number 1, all you had was the weight and the normal force. But here we have an additional force. We have this applied force. So the total of the downward forces have to equal the total of the upward forces. Well, the weight is not the only downward force. She's actually pushing down a little bit on this cart. So in addition to the weight that's pushing down on the floor, there is also a little bit of her push downward as well. Now the floor has to support both of those things in order to keep the net force 0 in the y direction. So the normal force again has to be the supporting force. So let me rewrite this, I'm sorry. So let's think about this in terms of F net remember the total of the forces, and that's what net means. F net is, let's pick a direction. Let's just say positive, let's go positive down. It doesn't matter, but let's just do that. The total of the forces in the y direction are F plus G plus F sub y. So again, I'm just going positive down, it doesn't matter. But this and this together are positive in my reference frame. And this one right here is in the negative direction, so plus and minus, or again, just say minus, you can sort of cut out the middleman. Now, these two work together and they are opposed by the normal force. And is this thing accelerating in the y direction? iPad says no, so does everybody else in the room, which is nobody. And so F net is 0, right? Because these things have to cancel each other out. So another way to think of this is that if F equals ma, then the a is 0, so of course F net is 0. That's another way if you want to think of it that way. So Fg plus Fy minus Fn. If you think about that logically, what that means is that this has to equal this. So mathematically, you can just bring it over here. So that means that the normal force must be the combination of those two things. And this is just a mathy, algebraic way to explain what I've already told you. And what should seem obvious, actually, is that all the downward forces have to be completely canceled by all the upward forces. In this case, we have 2 downward forces, we have 1 upward forces, and again, for like the 3rd time, they have to cancel each other out because this thing ain't accelerating in the y direction. So this is kind of an algebraic, mathy way to think about it. Again, we're trying to figure out what the normal force is, so let's just calculate. I'm just going to bring this up here. So the normal force must be equal to whatever the force of gravity was, which was 9.5 plus 5 times 9.8. That was your F sub g, remember? And now the y component here is going to be whatever 110 sine 30 is. Again, that's a sine component because we're looking for the opposite. That's where the trig comes in, right? That's why you have to be smart, is to understand the mix and the interplay of math and physics. So sine 110 sine 30. This would be your y component. And now whatever this number is, again, I don't know because I'm not going to calculate it, that would be your normal force. And so again, you can see here that the normal force has been adjusted because of the additional support it has to provide because the woman's pushing down a little bit. So like weight is always basically just mg, but the normal force will adjust depending on the force that's applied. So that takes care of the normal force. Now we're interested in the frictional force and the acceleration. So let's go blue. The frictional force. The first thing is, let's just write the generic formula for the frictional force. It is always mu times the normal force. The greater the normal force, the greater the friction. It makes perfect sense because the frictional force that keeps this book from sliding is a little bit, but not too hard if I push it sideways. However, if I start to push down on this book, the frictional force increases. The frictional force increases on that book because I am increasing the normal force, the normal force on this book. Because the harder I push down, the more the normal force has to increase to counteract that, because this book is not accelerating in the y direction. So the more force downward, the more normal force the table has to provide. So yeah, things that have greater normal forces have greater friction. Makes perfect sense. If you think about it, the heavier the car, the less likely it is to get stuck in the snow. Okay, so remember, we were trying to figure out the frictional force, just the total frictional force. Okay, well, the mu was given, so that's nice. The normal force was calculated. Hey, you pat yourself in the back. So it looks like this is just a straight up, okay, we're pretty much gonna be done. So 0.14 times whatever 14.5 times 9.8 is plus 110 sine 30. So this would be, again, the normal force is this and this together. That's why I have it right here. I just brought this whole thing down. And remember that frictional forces are negative forces. So whatever that number is, you're going to make sure you stick a negative on there. Because that would be how you get the frictional force. And it's negative. Okay. Now, last but not least, the acceleration of the carriage. Okay, so if you think about this, if you take a step back and just think about what's happening here. You have a woman pushing her cart at an angle here. Some of that force is in this direction. Friction is going to oppose this force right here. But the key here is that the motion of this cart is only in the x direction. So we will only consider x directional forces when considering the acceleration in the x direction. Okay, so what are our x directional forces? So I'm going to start with F net, but I'm going to kind of be specific about it. I'm going to say in the x direction, just to be super obvious about it. Hit you over the head with a sledgehammer with it. Well, there are really only two forces in the x direction. There's the frictional force and the horizontal component to her force. These are the only two forces that can affect the motion in the x direction. So F net, and I'm just going to pick a reference frame. I'm going to say positive this way because the carriage is moving that way. So why not? Again, it just doesn't. You can do it the other way, but why? Let's work smarter, not harder. So the F net is going to be whatever Fx was minus the force of friction. Again, I know that the question is asking for acceleration, but remember that the F net is equal to ma. So if we know F, then we know m, we can get a. So I'm just dealing with forces right now. I'll bring it back to acceleration in a moment. So Fx is not too hard. It's going to be 110 cos 30. We're going to subtract off the force of friction. We're subtracting it because it is a negative force. You could also think of it as, if you want to, that you always add all your forces together, but sometimes the forces are negative, so technically you're adding a negative. However you want to think about it is fine. I'm just putting the negative right here because I'm really adding these two forces together. It just happens to be that one is a negative force. So, well, this frictional force was whatever this was. And again, I'm not calculating this. You will calculate this. Even my iPad agrees that you should do some work. So 14.5 times 9.8 plus 110 sine 30. This again is the frictional force brought down to here. So all of this, these are two forces in the x direction. All of this will be equal to the ma in the x direction. Let's just, I'm not going to calculate this out, but let's just, for argument's sake, let's just, well, you know, whatever. Whatever this is. Let's put an arrow. Whatever that is. So if you want A, that means that all you got to do is divide by the mass, which in this case, the mass was 14.5. It was the 9.5 plus the 5, right? So 14.5. So that will get you your acceleration, and you're guaranteed, I can tell you right now, without even calculating, you're going to have a positive value because I know I've set the physics up correctly, that this will be a positive value on the numerator, and so you're going to end up with some value meters per second squared. And that's how you would get the acceleration. Any questions? No? Well, clearly I did an awesome job of explaining this. That's why there are no questions. So that was number 7 on Wednesday's assignment. The mother pushing a very, very large, fat baby along the street.